where we discuss the work. So we want to continue from there. We want to look at energy. Now, I told you that these three words or terms are interrelated. We talk about work and then energy and power. They are interrelated. So when you talk about energy, energy of a system is a measure of the ability to do work or of the system to do work. Okay. So let's say the energy of the system, the definition of energy is that the energy of a system is the ability of the system to do it. The ability of the system to do work. Okay. So energy can exist in so many forms. In so many forms, or in many forms. But here, our concern is on the mechanical energy. Okay, so we will be looking at mechanical energy of the system. Now, when you talk about mechanical energy, is the sum of what? The kinetic energy and that of the
potential.
Potential. Good. Sum of kinetic energy and then potential energy. Okay. So that is what we'll be considering. So we can say that the mechanical energy, at times you see it as E or T. That shows that that is equals to T. Okay, let me use KE. So that is equals to KE plus PE. Okay, so this is the total energy. So the mechanical energy can also be called the total energy of the system. Total energy of the system. Okay. So that is what we mean by a mechanical energy. Now, we will now pick these energies, that is the kinetic energy and then the potential energy. We'll look at the definitions of these energies. So now, when you talk about the kinetic energy, of a system. So the kinetic energy is the energy that the body possesses by virtue of what? Its motion. Okay. So when the object is in the motion, the energy that you'll be measuring or recording is what we term as what? The kinetic energy. So you say this is the energy possessed by a body, or a body possesses by a body. By virtue of its motion. That is a kinetic energy. So if we suppose that, suppose a constant force acts on an object. Okay, it acts on an object and then causes this object. Causes the object to accelerate. Through a distance s. So let's say through a distance s. So let's give a force F. Okay. So through a distance s, increasing the speed once there is an acceleration means that the object initially has a velocity, and as time goes on, its velocity changes to a second velocity. So increasing the speed from initial value u2 to a final value v. Now we can say that the work that is going to be done by that force on the object by the force is given us. So we'll say our work done is equals to force times distance. Okay, so now if we know that our force is equals to MA, and we substitute this to the work done equation, we will now have our work done to be expressed as work done to be equals to the force is mass times acceleration, then times our s. Okay, but from the constant acceleration equation, we know that acceleration equation, that is from the Newton's equation of motion, we know from this that v squared is equals to u squared plus 2a s. All right, so we can make a the subject here. So doing that, our 2as will be equals to v squared by taking the u squared to the other side of the equal sign, make it negative u squared. Then our inference, if we make a the subject, we will divide by 2s divided here by 2s. So it means our a is equals to v squared minus u squared all divided by 2s. That will go and then substitute our acceleration expression to the work done equation, this. So if we substitute equation star to equation star, we will now have our work done to be equal to, we have our mass. Now instead of the acceleration, we'll put v squared minus u squared all divided by 2a. Then multiply by our s. Sorry, 2s, not a. Yes, s. So multiply by our s. Now s will do away with this s. Then when we expand the bracket, by expanding it, our work done will be equals to, we have mass times v, that will be m V square minus mu square, and everything is divided by 2. So this can be written as half mv square minus half mu square. So you have this one there. Okay, but we know that the expression for kinetic energy is nothing but half mv square. So it means that I can write my change in kinetic energy. That is, so this is just a normal expression, but if you have a change in the kinetic energy where your velocity is varying, so that is going to be half mv square minus half mu square. So it means that half mu square, mv square minus half mu square is nothing but change in what? Kinetic energy. Okay, so this part is changing kinetic energy. So we can say that the work done is the same thing as what? Change so work done is the same thing as change in kinetic energy. Okay, and this is what we call the energy and then work relationship. So this is a relationship between work and then energy. So you can actually determine the work done by an object if you have an information by the energy possessed by the object. Okay, so if you know the change in kinetic energy, then you can use it to calculate the work done. So which means that it's not all cases that you will be given force and then distance or displacement and ask you to calculate for work done. They can give you a question which talks about the energy and then the work done. So once you have velocity, final velocity, and initial velocity, and then they're asking for the work done, then you need to write this relation down. You need to state that the work done is equals to what? Change in kinetic energy. Then you use that relation. Once you know the change in kinetic energy, then you can equate it to the work done. So that is the relation. So you take note of this equation here. Now you can also, so this is in a case of a constant force. Okay, you can also have it in terms of a variable force. Okay. So what I'm saying is the relationship between, oh, what did I write? Is a relationship between I think someone's microphone is on. If you can mute yourself, it'll help us. Oh, thank you. Between work done, and then kinetic energy. So that is the work principle. The work principle. And it states that the work done on an object is equal to increase in kinetic energy. Of the object. Okay. So let's also look at it in the case of a variable force. Now, when you take a variable force, now the work done will be that. So let's say we have our Cartesian plane. Okay, so let me say work done. Work energy relations on a variable force. Okay, so when we represent this on our Cartesian plane, so we have our z direction, we have our x direction, and our y. Now we have our curve. So once the force is varying, it means that the path is not going to be a straight line, but it will be in a curve-like format. So let's say we have something in this nature that is indicating the displacement or the path that the object has been moved through. So we have our position vector drawn through the origin to the path. So this is R. Then there was second R1, it is varying. The second position vector is connected to this one, let's say here. Obviously, you see that the second position vector is longer than the first one. So this will be R plus a certain change. Maybe it can be change of R. You can write it that way. Now, this distance here, this distance will now be our D, or this distance. So this is our D. Okay. So let's say the object has been moved from P1 to P2, that is 0.1 to 0.2. So we can now write our equation as this. You can say that the work done will be equals to, and I explain why we use integral. So let's say, okay, in short, once I'm going to write it here, let me just say R and then R2. So this is R1 and this is R2. So take it from R1, that's a lower limit, to R2, which is the upper limit. Just a minute, just a minute. Fine, fine, on your side. Yeah. Okay. Okay. Well, let me finish and see the way forward. Right. Okay, so let's proceed this. Now we take it from the lower limit to the upper limit. Then we have the force of R times the R. Okay, so you can, if you don't want to confuse yourself, make it R. So, but if I move FR means it's talking about a variable force. Okay, now because we are not having a straight path line here, we cannot use the normal multiplication. We need to divide this curve into a smaller divisions by finding the gradient. So that is why we are using the R. So this is the same thing as we now take it from the integral of R1 to R2. Then we substitute the expression for our F, then dot dr. So we substitute our acceleration expression as we saw back. Then when we do that, we will have, so let me say the work done is equal to integral of R1 to R2. Then M, we know that acceleration is nothing but what? Change in velocity respect to time. Okay, that is what we saw earlier on. When we differentiate velocity with respect to time or divide velocity with time, you get acceleration. So we make that substitution here. So instead of the A, we'll now write the V dt, then times our dr. That is what we will have. Now we need to change the limit. We need to change the limit to V, and then because here is R and then we are having V. So we need to do that. So by doing that, if you shift the A, the T to the R, because we know the R dt is what? V. Okay, so when you do that, this will give you integral of, now the limit will now change from V1 to V2. Then we'll have our M dr dt, dr dt on dv. Okay, so you are changing the limits here. You just shift this to the dr, so it will be dr on the t. Then this one will make the dv, but we know that the r on the t is what? V. Okay, so we'll now have it in terms of what? V. Okay, so we do the integration. After doing that, we'll have this to now be equals to, after you integrate this, okay, let me write it, then you see it. So integral of V1 to V2, now we have M, this is V, it's not more the RDT, so MV dV. So when you integrate this, so if I'm integrating X, that will be X squared on 2, okay? So it means that the integral of this is going to be MV squared divided by the power, but I'm taking the limit from V1 to V2. So you substitute the upper limit minus the lower limit. So that's going to be half M open bracket. My V will now be V1, so V2 by a square. So V2 squared minus V1 squared. Okay. So if you expand it, it will give you half mv2 square minus half mv1 squared. So you see that in terms of the variable force, the principle is still valid. You still have this for the variable force. Okay, so kindly take note of it, how you get a work out from energy. All right, so let's look at conservative force field. You look at in your manual, you get some example. You go through them since we are not having enough time for me to be going through the example with you, but they are solved, so you go through, you understand them. So we are now looking at conservative force field. Yeah, so let me make this conservative and non-conservative. Conservative forces. Okay, so if you want to check whether the force that is using to do the work is conserved, okay, so you need to understand the kind of force that is being applied. Now, some forces doesn't, or some force don't depend on the path that the object takes to do the work. And those forces are what we coin them as what? Conservative force field. So a force is said to be conservative if the work done by the force is path independent, but depends solely on the final and then the initial positions of the object. Okay. So for instance, when you talk about conservative force field in a layman view, so you have two places that you want. You are at town A and you want to move to town B. So there are a lot of roads that are linking to town B. So we are not concerned about which path that you will take to arrive at what town B. The only thing we are looking at that you should be able to move from town A to B. That is our focus. So what I'm just trying to say is that if this is town A and then this is B, there is a direct path that is linking A and B. There is a path that you pass here to maybe town C. Then from town C, you come to town B. Somebody can decide to go somewhere and then finally back to B. So for the force to be a conservative force field, our concern is not like somebody has used a longer path than the other. We are only looking at the initial and then the final locations. We are not care about what the path that you take to do. So the work done is independent of path taken. So that is one property about a conservative force field. So it's path independent, but depends on what the initial and then the final positions. Then again, the curl of the force is 0. So when you find the curl of every conservative force field, it must give you 0. Aside that, those forces are not classified or considered as a conservative force field. Okay. Do you understand what I've said?
Yes, sir. You have understood.
Yes, sir.
Okay. So under the conservative force field, I'm just giving or let me make it this way. So let me just say properties of conservative force fields. So one, you're saying that they are path independent. Then secondly, they only depends on the initial and final position. Then thirdly, talk about the curl of the force is 0. So if you have any of these three coming in, means that the force is a conservative force field. So it means the non-conservative forces do not have these properties. So if it is otherwise from these ones, it means that that force field is what? A non-conservative force field. Now you can talk about the example of a conservative force field. So once we are saying that they are position dependent, so you can say example. Now you can talk about the Coulombic force. You talk about the Newton universal force. Newton gravitational force. Gravitational force. Okay. Talk about the gravitational force. So you can write these one as conservative force field. But any other force will be classified as a non-conservative. Any other force will be classified as a non-conservative. And then those forces are known as what? The dissipative force. So when you say dissipative, means that they produce heat at the end of it. And one common example we can talk about is the friction, tension, any other force apart from these forces that I've mentioned is a non-conservative force field. So once we are saying that, you see, when you write your Coulombic force, you say the F is equals to K, when you are dealing with the charges, so K1, Q2 on R squared. So since you are not dealing with this position, so you are saying that your force is what? Conservative. We also talk about the gravitational force. So let's say FC. So the gravitational force, so Fg is equals to chain M1, M2 over R square. So once it is not dependent on the R, you will say that as the distance is increasing, the force is decreasing low. So you will presume that the force along all the path is constant. So you are not looking at the longest distance or the shortest distance that the object takes to do the work. Okay, so these are few examples of the conservative force field. The rest are non-conservative. Okay, so that is it. I will pick the yeah. So you can also talk about this one. Let me add this too.
Hello, sir.
Yes.
Sir, is a magnetic force also a consecutive force? An example of conservative force.
It's non-conservative. It's a magnetic force. It's a non because it has no R relating to it. It's a non. Okay, so the other one you can talk about is so let's say the fourth example property. The fourth property is that the force field is conservative if and only if for any simple closed non-intersection curve. Okay, so if a work done in a closed loop, okay, the work done by the force. Let me say this. If the work done by the force in a closed loop is the work done by the force in a closed loop is zero. Loop is zero. So it also be a conservative force. So for instance, once we are talking about a closed loop, this is a closed loop. If you start at this particular point and you move around and come back to where you originally started your journey, you see that your displacement becomes zero. And once your displacement is zero, it means the work done will be zero. Okay, so you started at this A and then you finally come back to A. So like you are in your room, you move outside and then you come back to your room. So it like if somebody comes to see you in your room and the person moves away for some time, the person comes back to see you still in your room. That person wouldn't have known that you have gone out and come back. So it means that when you walk around a closed loop, your displacement becomes zero. So once your displacement is zero, then your work done will be zero. Okay, so that's why we're also saying that any work done on the closed loop will consider it as a conservative force. Okay, so let's look at the third property where we are saying that the curl of the force is zero. So let me take you back small. So when you say the curl of the force is zero, it simply means that when you take the number cross with any other force, and this is giving you zero, it means that it's a conservative force field. So the last one is also when we take the integral of this, the R, and it's also zero. So that is the meaning. So we'll look at an example, what we mean by a conservative force field. So with that one, I will go through an example with you, and then you go and then look for some questions and then. So, example. Show that the force field F defined by F is equals to y squared z keep minus 6xz square, all is along the I direction, then plus 2xyz keep along the j direction, plus we have 3xy square z square minus 6x square z. Then this is along the k. It's conservative. Conservative. Okay, so this is the question. The question is saying that you should show that the force that is defined by this expression is a conservative force field. So solution. You first of all give a condition. Since we know that one of the properties of a conservative force field is the curl of the force is 0. The third property. Okay. You first invoke or impose that condition to your field. You presume that the force field is conservative. Okay. So you can say for the force F to be a conservative force field, for the force F to be conservative, then the curl of the force must be 0 or is 0. Okay, so there's a condition. So you are saying that curl of this force should give you 0. Okay, so proceeding from this point, first of all, define your number. This is del on del x I plus del on del y j plus del on del z in the k. Okay, so once you have it in the curl form, you have to put it in a matrix form. So we define our curl, then we get our force. So our force is also equals to, we have y squared z keep minus 6xz squared I plus 2xy z keep j plus, we have 3xy squared y squared z squared minus 6x squared. Please do down assign anything. Don't hesitate. Kindly draw my attention, okay? X squared z and then along the k. So we'll now put this there. So the curl of this should be 0, means that we'll have the matrix of this should be giving us 0. So first, my definition of the curl, we have del x, then here will be del y, then I have del z. Now I also write my force component, the I, j, and then k respectively as it is. So here will be my I, that will be y squared z keep, then minus 6xc squared, because the whole of this is along the I. So everything here should be along the I. Then the second term is J is what? 2x, y, z cube. So this is also along the J. Then lastly, my K part is 3x y squared minus 6x squared z. Then I'll put my matrix. So the determinant of whatever you are finding must give us the, okay. Now we've defined this. We now need to find the determinant. And you remember when we're dealing with the vectors, you first of all consider the first column. So columns, we have 3 columns. Column 1, column 2, column 3. Rows, we also have 3. Row 1, row 2, row 3. So let's start by considering the first column. So you presume that the first column is not there. First column, then the first row are not there. So you are left with 2 by 2 matrix to find the determinant, the difference. So this side is gone. So we are left with dy, dy, 2xy z cube, and then dy, ddz, 3xy squared minus 6x squared z. Yes, so is someone raising the hand? Yes.
Yes, please.
Okay, go ahead.
So please, the key.
Okay.
And we have 3x y square z square.
Mhm.
But if the
okay.
one that is root, that one did not go.
Thank you. It's
Welcome.
on the side. Thank you for that. So there is Z there. So it's 3 x y z square. So this square. All right, thank you. Now we will start by taking that. So when we cancel them out, we'll be left with del on del y, taking with 3xy squared z squared c squared minus 6x squared y not c c. So this is what we'll have. Then minus. Then we'll left with del on del z, taking with, we have 2x y z cube, 2x y z cube. Now everything here is along the I, so we bring the direction. So let me come back here. This is what I am saying. So presume that this is off, this is off. Then you take the diagonal multiple. So this one will come and take this minus this one of that. So that is what I did there. Okay, so we have del y taking or operating on this part minus del z also operating on that part. Okay, so that gives us the I direction because we cancel the I column. So this column has been cancelled. So when you are done, we come back. Don't forget what I told you the other time. I said the sign alternate. We have positive, negative, positive. Okay, so we are done with the first positive. We come to negative. That's the second thing. So when you come here, it presumes that we are canceling the second column. So this one will be cancelled. So if this is cancelled, we'll left with this part, we'll be left with this part, and then this part. So when we do that, we will do the same diagonal multiple. So this will take whatever that is here and this one will also take whatever that is here, the difference. Okay, you take the first one, the first del on this part minus the second del on that part. So that's what we are also going to do. So in that case, we'll be left with del x will be taking 3x y squared z squared blah blah on up to the sorry. So but it's minus, so we'll take our minus sign. So minus open bracket, we have del on del x taking 3x y squared z squared minus 6x z, then minus, then we are taking with this del z on this. So minus del on del z taking on y squared z keep taking on y squared z keep minus 6x z squared z squared close bracket, then your big bracket along the j. Then you come to the next one, which is a plus. Open your bigger bracket. So let's come back here. So this time around, we are on the last column. So it means that we are canceling this. So we are crossing this. So that's why we're using this plus. So when you cross this one, we'll be left with this. So del x, we take 2x that, and then this one will also take this down. Okay, so let's go to the next slide and do it. So this would be del x operating on 2x y z keep, then minus, we are taking del y on first time del y. So this will be close the bracket. So minus del y on, we have the time y squared, we have y squared c keep minus 6xz squared, and then k. Let me check the first time. Okay, so this is what we have. So what we are now saying is that when we sum everything here, summing all these terms together, we should get 0. So when you do that and you're having 0, then you conclude by saying that your based on your preambles that you set, because you set for a conservative force field, the curl of it must be 0. But when you sum up and the answer is not giving you 0, you also conclude denying the preamble that you first set. So which means that that force field is not a conservative force field. So now let's operate on one by expanding. We are differentiating the first term here up. We are differentiating with respect to y. So let's do our differentiation. So when we differentiate y squared, we'll get 6, 2y. So 2y multiplied by 2 will give us 6. So this will give us 6x y z squared. This is what you will get if you differentiate this part with respect to y. Then we differentiate the second part with respect to y, gives us 0, because there is no y term here. So this one will be minus 0. Then we'll come to the second term. There's minus sign there, minus. Then we differentiate this term with respect to z. So when we do that, we are differentiating z. When we differentiate z keep, you get 3z squared. So 3 by 2 will give us 6. So this will give us 6 x, y, z squared. So this is what you have. Then everything is along the I. Then we'll come to the next term here, which is minus. So minus, open bracket. The first term here, we are differentiating with respect to x. So when we differentiate this one with respect to x, we'll have 3. So 3y squared z squared. So this will be 3y squared z squared. That's this term. Then we'll come to the second term here. This one will be x again. We differentiate this one with respect to x. So that gives us 12. So 12x yz. So this one will be minus 12x z. Okay. Then you minus this term. So minus. Then we differentiate this one with respect to z. Look at this. So I differentiate z, keep you get 3. So that would be 3y squared z squared. So 3y squared z squared. Then this is operating on that. So this negative will make this one positive. So negative is positive. So we have plus. Let me write it here. So we are in the same bracket. So let me make the bracket big and then write it. So this, that, make it plus. So plus. Then we differentiate this one respect to z. That will give us 12xz. So that will be plus 12x and then z. Then we'll close our bracket. Then that takes the j direction. Okay, so let's continue with the last one. So plus here. The last one is this. We are differentiating this one with respect to x. So that is going to be 2yz keep minus. Minus, we differentiate with respect to y. That will be 2yz keep. Then this is negative. That should be plus. Then we differentiate with respect to y. There's no y terms here, so this becomes 0. Then we put our k direction here. Now let's simplify each bracket. So simplifying the bracket, we have 6xyz squared, then minus 6xyz squared. So they will cancel out. So whatever that is here is 0. Let's come to the second term. We have 3y squared z squared. Then we have 3y squared z squared. But this is positive, this is negative. They will cancel out. Then we have minus 12xz. We have plus 12xz. So this will also do away with that. Then let's come to the last part. 2yz keep minus 2yz keep will also go away. So it means that when we found the curl of it, all that we have is we have the curl of the force that we found is equals to 0i plus 0j plus 0k. Okay, then which means the curl of the force is 0. And since the curl of the force is 0, we conclude by saying that the force is what? A conservative force field. So in conclusion, so since the curl of the force field or the force that is the same thing of the force field is 0, then the vector field or the force, the vector field F is a conservative force field. Okay, so that is how you do it. Do we understand?
Yes, sir.
Yes, sir.
I believe when you see something like this, you can do it.
So this one, if this one want to come, is it full question or there'll be another babies added to it? So this one
Hey,
alone.
how can we give you this one just as a full question? This is too small to be a full question.
Oh, I'm done.
Okay, so let's proceed. Now we are done with the kinetic energy. Let's also look at potential energy. We know we said the energy we are looking at is the mechanical energy, which comprises of kinetic and then potential. So we are done with the kinetic part. We are looking at the potential part. So the potential energy of a body is the energy the body possesses well possesses. If you first check with the spelling. Possess, I think there is another SSPES. You check it possesses by virtue of its position. Okay, so that is the potential energy. An example is when you throw an object up, it's thrown vertically up. Okay, you have a potential energy. What happened is that at your hand level, there is no position or height of that ball. So the potential energy there becomes zero. So as you send the ball into the air, it starts to increase. So the height is increasing. So once the height is increasing, then the potential energy is increasing. So you can write the potential energy as mgh. So all these, so this is a constant term. Mass is constant, gravity is constant. So the only varying parameter is the height. Okay, so that is what. So it depends on only the height. So with a longer height or a higher height means potential energy is going to be high. If the height is also less or low, you also have what? A less potential energy. Now, but you and I believe that when something is being thrown vertically up to the air, it attains what we call the maximum height. So when it gets to its maximum height, it's stop momentarily, like you will not see the stopping, but it has to come to a rest before it begins to come down again. So anything that is thrown up must come down, because when the energy is increased to its maximum, once it's reached its maximum, then it cannot go beyond that energy range again. So it must come down. Okay, so within the okay, so within that we have what we call the gravitational potential energy within that, and we have another form of the potential energy as well, elastic potential energy. So these are the other potential energy that we'll talk about and you need to know. So within the potential energy, you have other energy we call the gravitational potential. Potential energy. And then we have the elastic potential energy. So we have these categories of potential energies. Okay, so let's see what happens if you mention a gravitational potential energy. So it means that that energy depends solely on the height, because it's being thrown vertically up. Okay, and gravity has an effect on that object. So that is why the name implies that gravitational potential energy. So under the gravitational potential energy, so that is GPE. So this is the energy that the body possesses as a result of its position with reference to the Earth's surface, okay, because of the gravity. So this is the energy the body possesses the energy possesses. This is the energy possessed by an object by virtue of its position, with reference to the earth, surface. Okay. So now let's say we have an object being thrown. Suppose we throw an object. Now we have this to be our initial. So since we are dealing with height, we are dealing with the y, the vertical part, that's the y. So let me give this one as yi and this one as yf, which is my initial and then final positions. So the difference between this will give me my height. So that will be my height. Now, as the object is thrown, the object is going up. Now we'll have gravity, which is going down, and this is minus g. So the gravity is always negative as it's going down. As the object is going up, then the gravity will be pulling it down, which is minus negative. Remember, we are saying that the force is equals to ma. If the force and then the distance are moving the same direction. Okay, but because the force that is pulling the object up is vertical and then the gravity is going down, that's why we have the negative. They are moving in the opposite direction. So that's why the gene becomes the negative. Okay, so we have this gene in the opposite direction going down like that. Now the work done by the work done against gravity. Against gravity will be expressed as this. So W will be equals to F cos theta times D. We saw this formula earlier. Then substituting what we have in this diagram, so we will get our work done to be this. So we have M gen H from this formula, which is the same as M gen in bracket. We'll have the final position minus the initial position. Then their difference is what? H. So which means we have our M gen H to be our gravitational potential, or the work done against the gravity. Okay. So that is work done against the gravity. If we also look at work done by gravity, so we just talk about the work done by the gravity. In that case, you will have the force of gravity doing everything. So that is what is going to do the work. So your work done will be equals to negative of M gen into bracket YF minus YI. This is work done by gravity. So in that case, if I push my negative inside the bracket, I'm going to have M gen in bracket. That will be YI minus YF. And this will give us a negative work done. So when you have a negative work done, it means that the work that is done is by gravity. If you have a positive work done, it means that the work done is against gravity. So take note. This will give us a negative because the initial height is lower than the final height. So when you subtract a bigger number from a smaller number, then it gives you a negative value. So this makes work done negative, which we are saying that in that case, work is only done by the gravity. But for the first part, work is done against gravity, and for that matter, we have positive work done. Okay, exactly, please. As usual, as we saw it for the kinetic energy, we can also have it, yes. Yeah, Charles, go ahead. Yeah, go ahead, please. Go ahead with the question, Charles.
Please, I'm a bit confused with regards to the YF and then the YI. So if you can please take it again for me.
Okay. So what we are saying here is, see, when you want your work to be done against gravity, and work done against gravity means that you are throwing something vertically up. So if that object is going up, it is against the gravitational pull. Gravity normally acts downward. Then the work is trying to, or the object is trying to do work to overcome the gravity. So that's why we are saying that the work is done against. So as the work done, since we saw that potential energy is mgh. So otherwise, in other words, let me just say mg yi. Then the work done here will be mg yf. So let's give a height. So let's say here is 1 and here is 2. You see that 2 is greater than 1. So if I take 2 minus 1, that will give me positive 1. Then if I substitute positive 1 here, because I know that this is equals to h is equals to their difference. So if I write my energy as m Jane h, and h is 1, definitely my work done will be plus. So in that case, the object is going vertically up. So you are doing work against gravity. But in the case that you drop something down, so in this case, you are going down. And when you drop something down, there is nothing that is pulling that thing to go down. It only comes down by the gravitational pull. Okay, so as it's going down, there is no work, no force is being given to it. I don't know whether you're following. So that's what we're saying, that in that case, work is now be done by gravity, the gravity that is now causing the work or the object to move down. So,
Okay.
So in that point, you are going to have, you are already on the height. So your initial now become 2. Okay, but we always take final minus initial. So in that case, your final point will be your y1. So it will now be 1 minus 2. And 1 minus 2 will give you negative 1. So when your h become negative 1, in that case, we have mj minus h. And this gives you minus mj h. And that's why we are saying that this is work done by gravity. So work done by gravity simply means you are at a height and you drop something vertically down. Maybe you are in a story building and you throw something down. When you drop that thing, there is no force that is acting on that thing apart from the gravitational force or the gravitational pull. Is that okay?
Yeah. Yes, please.
All right.
Thank you.
Most welcome. Okay, so as usual, we saw on the kinetic energy, we also have a variable force. We can also write it in the form of a variable force. So when you take the gravitational force, let me say change, signify gravitational force, and we're saying that it's negative change in V, that's the potential. The V is nothing but potential. So please mute yourself. Mute yourself. All right, thank you. So now, in the potential talks about positions. So if you have an object that is being moved from R1 to the R2, as we see. Now, when you define a gravitational potential, say gravitational potential is the work done in bringing a unit object from an infinity to that point. Okay, the gravitational potential about a point is the work done in bringing what a unit charge from what an infinity to that point. Okay, so you will use that to establish it. So if I have this, then I can put it in the R region like this. So as I said, so if I'm finding the potential at this point, so the work that I use to bring an object which is at the far to this point will be my gravitational potential. So this one will be maybe I1 and then R2. Okay, so I will take my integral here. So this will now be equal to the integral negative, but this is already negative. Then I will have my W chain dot, oh, sorry, this should be potential. Let's define potential and write the work done. So the potential is what? The work done. So this one dot R, and I'm taking R1 to R2, or it can be R0 to R1. So as usual, when you differentiate, you integrate this one, you're going to have your potential to be equals to, you have your minus work done, then multiply by R2 minus R1, and that is your potential, vertical potential. Then when you write the GPE, which we call the gravitational potential, that one will also be in the vertical part. So mg be YF minus YI, and that gives you our mgh, which is your h. So these are the definition for the two potential. So this is for the gravitational potential. Now the elastic potential is the potential that we gain from elastic materials. It can be a spring, it can be a rubber tie. Okay, so that will give us our elastic potential energy. So if we look at the elastic potential energy, elastic potential energy. So this is the second form of the potential energy, and as I said, this form of potential is obtained from an elastic material. Now, when you cast your mind back to Hooke's law, which says that provided that the elastic medium is not exceeded, the force applied to the elastic material, the extension will be equal to the extension, or the extension will be the same as the force applied. So that is F is equals to minus K X or E, depending on whichever letter you're using for your extension. So that is Hooke's law. Now this negative sign is telling us that a force is what? A restoring force. A restoring force in the sense that when you stretch a spring, you see that the moment you stretch a spring, the spring wants to regain its original length. So by doing so, you see that there will be a force. The force from the spring will try to bring the spring back to its original position, but you've already stretched it in the opposite direction. So you see the force and then the extension will be acting in opposite direction. So that is why we have the negative sign telling us that the force is a restoring force, or in other words, the force acts in opposite to the displacement. Okay. So we can say the first law of the spring is called Hooke's law. And it is expressed as F is equals to minus K X. Okay. So where F is the applied force, K is spring constant, and then X is extension. So, in short, Hooke's law says that provided provided an elastic limit does not exceed the force applied is proportional to the extension. Okay. So that is our result. Now, if we take an elastic material like a spring, now one end of the spring is fixed and the other part is attached to a mass. Okay. So now that is the initial stage. So this is M. Now let's say we apply a force to this spring, and once we apply a force, we expect the spring to stretch to a certain length. So if I put this line here, this is X naught. So from X naught to this point will be our extension. That's what we are calling the X. So how much it has been increased. So now at this point, you will have your force to be pointing in this direction, because the spring will want to come back to this original length, but your displacement is going this way. Okay, so the S is going in the opposite direction. So once that happens, you will have your force to be equal to the negative kx. Okay, so this is an extension. That is when you stretch. You can also have compression that is coming in when you also compress a spring. So by compressing it, you have something like this. Oh, sorry. So when you compress it, you have something like this nature. So it's initially here, and then you compress this length. So at this case, force will be going in this way, and then this will be the direction of your displacement. Your displacement will be going this way because you are trying to bring it down, to compress it. So these are the cases. So here you realize that at this point, our X, that's extension, is 0 because nothing has been done. You've not applied any force, so there's no extension here. Then here, our extension X is greater than 0 because you stretch it. So you have a value which is greater than 0. But when you come here, our extension X is less than 0 because it's now moving towards the negative. Because if you consider this to be your origin, so 0, once you are moving in this direction, you are dealing with positive numbers. When you are going in the other side, you are dealing with negative numbers. So that's why we are saying that the X will be lower than what? 0. So to write our potential for this, we'll say, okay, so suppose that we pull we pull the block outwards. So we are pulling it outwards. Okay. By a displacement x. A displacement x. Then the work done. The work done by the spring force. By the spring force is given as this. It's given us, we have the work done to be equals to integral of 0 to x. Then we have force Tx because we are dealing with the x direction, the horizontal direction. So, but F is equals to minus Kx. So we do that substitution. So work done equals integral of 0 to x. Then we have minus Kx, then the x. So when we integrate this, this is going to give us minus Kx squared on 2. Then we take the limit from 0 to x. So when we do that, this will give us nothing but minus half Kx squared. So half Kx squared. That is why we have our potential to be given as that. So that's the elastic potential. Try energy of a spring or of the spring. The spring is E of x is equals to minus half Kx squared. This is our elastic potential energy. So one thing you should know is that the work is done by an external force, and that external force is by pulling the spring to the positive direction. So that is, and again, as I told you, work done by is what? Negative, and done against is positive. These are possible objective questions to confuse you. So you will see it and you will be confused.
Okay. Is it work done? I didn't hear. My line just.
Oh, okay. Go and find out. I'm stressing on work done against and work done by. So, you know, in the case, which scenario or situation do we say work is done by a system and work is done against a system? So I'm just stressing on it. Okay. So if I may ask you a question, what is the mechanical energy of an oscillatory system? So if you have a system that you allow the system to oscillate, so what happens to the mechanical energy? Does the mechanical energy change or remains constant? So what I'm saying here is that, you see, look at what we've done here. So assuming we stretch this spring and allow it to be oscillating. So what it will do is that it will go to this side, then try to relax. Okay. So after it has been stretched to this side, when you release your hand, it will try to relax. So by relaxing, it will come back and forth. Okay. So as it is moving that way, what will be the mechanical energy? So when it's happening like that, the mechanical energy will be constant. Okay. Because you will have the gravitational potential for the elastics in the form of kinetic, which is half kx squared. And then you also have the, the gravitational potential. So the gravitational potential will also be in the form of what? mgh or x, because now you also be dealing with x. So when you add those two together, you will have a constant mechanical energy. Mechanical energy will be constant, even value. Okay. So let's look at conservation of energy. Conservation of energy. So you need to know the principle of conservation of energy. Now, the principle of conservation of energy states that the total mechanical energy of a system remains constant. So that is what you should know. That is mechanical energy plus the potential energy is constant. So when you mean like constant, it's not necessarily means zero, but it's not varying, it's not changing. It's constant throughout. Okay. So the principle conservation of energy states that the mechanical energy or the total energy of a system remains constant. Are we there?
Yes, please.
Are we sure we are not sleeping?
We are not.
Okay. So what this statement is saying that, from the basic principle of physics, like we define that energy can neither be created nor destroyed, but can only be converted from one form of energy to another. And what it means is that the mechanical energy, there is no loss of the kinetic energy. So the kinetic energy will be changed to a potential energy in the system. So for instance, if you take a simple pendulum bob that is attached to one end is fixed, and then the other end is allowed to oscillate. So then you displace this one through a small angle like this. Now, when you release this one, you expect it to oscillate. So it will be moving to and then through. Now, you can see that if I take this level to the height, so this will give me my height. So this will be H. Oh, sorry, H, I'm writing H bar. I've been writing H bar, so I'm used to it. So H, then the same way. So this one will also be H. Oh, I am also H. Okay. So now this is what is going to happen. If you look at it here, what we define our energy. So we are saying that mechanical energy E is equals to KE plus P, which is half mv square plus mgh. So this is our E. Now, if you look at the positions of the object, so at this point, we can say that since potential energy is position dependent, so you can see at this point the particle has a maximum height here. So once it's at the maximum height, so we can have PE to be maximum at this point. Potential energy is maximum. Then kinetic energy is minimum. So its minimum will be 0. So what I mean is, look at the expression for the two energies. At the maximum height, the V becomes 0. So when V is 0, 0 times any number is 0. So which means that at this position, there is no kinetic energy. That tells us that the particle remains, or the particle is at rest. Okay, because we say kinetic energy is the energy possessed by a body by virtue of what its motion. So once it is not moving, it means there is no kinetic energy. So that is the meaning. Then along this curve, so you see that at this point, the kinetic energy is high. Sorry, potential is high, but kinetic is 0 or minimum. So when the particle is started moving along the curve, this curve, you see that the height will be decreasing. So let's say at this point, and at this point, you see that this is longer than this. So it means this will be a smaller potential, but the particle will begin to increase its velocity. So as the system loses potential energy, that energy is being converted or transferred to what? Kinetic energy. Okay, so within this, the particle will have both kinetic energy and then potential energy, and that will be the mechanical energy along this path. Now, when the particle gets to this position here, at this position, there is no height because H now becomes 0. So at this point, H is 0, which means that kinetic energy will be maximum. Will be maximum, then potential energy will be minimum. Potential will be minimum because there is no height here. But this point too, we have what? V is 0 at this point. So V is 0 at this point. The same way apply to the path. Here too, we have both kinetic plus potential along the path. When it gets to this point, the same thing as what has happened here. At this point too, V is 0. Then you still have your PE to be max, and then your KE to be minimum. So that is what we mean by the conservation of what? Energy. So energy is not lost, though there wouldn't be a kinetic energy at this point, but there is what? A potential energy. So the potential energy will also be lost by changing to what? Kinetic energy for the system. So that's why we say that a mechanical energy. So every system has what? Both kinetic and then potential, because they keep on switching. It will switch to kinetic, later switch to what? Potential. So that is the meaning of that. Yes.
Yeah, sir, please, with the law that is stated,
Okay.
is it the same as the one you just stated, like the energy cannot be created or destroyed, but can be converted from one form to? Is it the same as this one, the principle of
Oh, yes,
condensation,
yes,
the one you
yes.
just said?
They are same. They are the
Okay,
same thing. They
okay,
are the
okay.
same thing.
Thank you.
Lucky hand is up.
I'm the one who just spoke.
Ah, okay, 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 okay. All right.
Yes.
Thank you. So let's proceed. Okay. So that is it. So one way you can cite an example of the energy transformation is when you have a, a mango fruit hanging on the mango. So as the mango fruit is hanging, since it is not moving, there is no kinetic energy there. Now, when you pluck that mango, then the mango starts to come down. Then the potential energy that it was having on top start to change to kinetic. Then the mango will now be dropping, coming down gradually, gradually, and finally touches the ground. So the moment it touches the ground, then that kinetic energy is no more there, but that doesn't mean that it has been lost. It will be transformed to another form of energy. Once it touches the ground, you will hear sound. Sound is also a form of energy. So the kinetic energy will be converted to sound energy. Then there is going to be an impact between the mango and then the floor or the ground. Now, when there is an impact, heat will be generated. Okay, so it means that to be able to conserve that energy, it means that the kinetic energy split it into what? Sound and then what? Heat. You understand? So that means that there is no loss or gain of what? The energy of the system. The energy at the end of it all will still be the same thing, just that it has been changed to a different form of energy. All right, so that is what we need to understand here. So let's draw down this important equation. So work done on an object goes to increase its kinetic energy, as we have already talked about it. So we can say the work done, we've seen that there's no need. And then we also establish the fact that the total energy or the mechanical energy of the system is what? Constant, if the system is allowed to oscillate. So that is all about the energy. So let's look at power. All right, so power is the rate of doing work. Okay, so power is how much work you are able to do within a specific time. That is your power, your ability to do something at a specific time. So this can be written as power is equals to work done divided by time taken. So the moment you hear rate, means that it has been divided by time. So can bring this on, break it down. So power is equal to what is work done? Work done is force times distance. What about time? So which means that my force F times distance over T. And what is distance over T? But distance on T. Hello, somebody, microphone is on. Is equals to V. So I can also say power can be written as what? F multiplied by V. So dimensionally, when you take velocity multiplied by force, it will give you the unit of power. And the unit of power is, this one everybody know.
What?
So you're asking me a question. Or you're saying that the power, the unit of power is watt. So that's it. Okay. Somebody was teaching in the class and then the child was sleeping. So it's capital W. So this student was sleeping and the teacher wants to use it as a means of what? Punishing the student. So you know when you are sleeping and then they wake you up, at that moment you can't think, you can't reason. Then you just wake the student up and then threw the question to him. Hey you, what is the unit of power? And by then they were also teaching work, energy, and power. So the student didn't understand the question. So he wants to ask for clarification. So he says, what? So say what? The teacher thought like he has answered the question because the unit of power is what? Is watts. Then the teacher said, oh, they should clap for him. So the student was surprised. He was surprised why he was asked to be clapped for. But that's it. Okay, so
That one is divine intervention.
divine intervention. This will happen in your quiz. So. So that is it about power. So if I understand power, like how we use our electrical appliances, various homes, you can always calculate for the cost. Because if you know that this particular instrument consumes electricity, this amount of electricity for this number of days or this period, then you can calculate how much it will cost you when you use that particular appliance. And that is what they do in the VRA offices, and they will bring out our bill, those who are using the post meter. So at the end of the month, they will look at how much power you consume. Then use the price, and then they'll come out with your total bill. Okay, so that is that for our energy, work, and then power. So the next thing we would have looked at is the section 3, which is the linear momentum and then collision, which is what we were taught last week. So there will be a need for us to go through that. Maybe if you don't understand something and then you have a question on that hand, aside that, can't go over it. So we'll move to the next. Let's see if you can remind me where you've got into last week. Yes, please.
Hello, sir.
Yeah, yes, please. I was reading about the power, and I came across one word,
Okay.
horsepower,
Horsepower.
that is used by by the British or the Americans, something like that.
Mhm.
Can you elaborate on that for us?
Yeah. So the horsepower talks about capacity, the engine capacity. Okay, so every when it comes to the mechanics, every machine that is designed has its capacity, and that will give you an idea about the consumption rate of that engine. Okay, so that is just a unit of measurement for the power. So as you are dealing with an engine, how much um, diesel or fuel that the engine takes. Okay, so when you want to buy any machinery, you look at the horsepower. Mhm. And you know that the higher the horsepower, it means that the higher the consumption. Mhm. So that's how it's been defined. It's just a unit of measurement. In the machinery, maybe a car, they will say like one is 1.5 and it's like 2 point something. These are the capacity, the unit telling you the capacity of the car or the engine in that car. That okay?
Okay, sir. So it's just like motorbike. If you are going to
Yes,
buy a motorbike, we have the 125, we have the
yes,
150,
uh-huh.
and the 200. Yeah, the
Yeah,
200, they have higher engine capacity and can run faster,
faster
meaning
good
they consume more fuel.
fuel. Mm.
Oh, okay. All right, sir. Thank you.
So where did you end last week on the momentum? Let me just pick it from there.
I think we did elastic collision and then inelastic.
Yes. So that's the section 4. So it means that you're done with section 4. Oh, and so you told me the other time, but I forgot the exact point.
But we didn't. He escaped some part. I mean, the latter part. I don't know. Is it coefficient or something like that?
Coefficient
Something.
of
He said he would.
Restitution.
coefficient of
Something
restitution.
like that. Yes, sir.
Oh, okay. So that one, see, when you are calculating collisions for elastic, especially when you are dealing with elastic collision. Elastic collision, both momentum and what kinetic energy are conserved. So you need to get an equation for the momentum part and also get an equation for the kinetic energy. Now, when you solve those two equations simultaneously, maybe probably you are asked to find the final velocity or the initial velocity of one part. Okay, so you need to get two equations simultaneously. Then you solve it. So using those that method is very, very long, and then it's time consuming. When you don't even take time, you can't simplify or factorize your terms well. Then there's a need for you to use the coefficient of restitution. So the coefficient of restitution is kind of simple and then short. So the coefficient of restitution is nothing but when you take the velocity of approach is equal to the negative velocity of what separation. So this is the formula for coefficient of restitution. So it says what the velocities of approach is equals to the negative of velocities of what? Separation. I'm not teaching this, I just want to show it to you. Velocity of separation. Separation. Okay, so what this means is that the relative velocity is relative velocity of approach. It is relative. Relative velocity of approach is equals to the negative relative of relative velocity of separation. Okay, so look at this up here in short, simple terms. Here we have body A, or let's say body 1. We have another body 2. Now this body has mass m1. This body has mass m2. Let's say this is initially moving with u1. This is moving with u2. Then after collision, since it's elastic, the bodies separate and move with what? Different velocities. Now, this sketch is not like it doesn't have a format of sketching. So after solving for whatever you want, at the end of it all, that's why you will know whether after separating mass 2 is moving opposite to its initial direction or not. So don't worry about the sketch. So just sketch it the way you want. After that, you will see the answer will tell you the direction at which they are moving after the collision, because you will not know. Maybe after collision, they all move to the left, they all move to the right, or they are moving like the way I've sketched it here. So you can just sketch it in any format you want. So this is your 1, so this will be P1. Then this one will be your M1, still M1, because they are constants. Okay, so now you impose the conservation of what? Linear momentum. So that since this is elastic, so we said for elastic collision, both momentum and kinetic energy are conserved. Okay, so now you write the formula for the momentum and then the kinetic energy. So for that, we are saying that M1 collision before. So you're saying that collision before, no, momentum before collision. Let me just put it that way. Momentum before collision is equals to momentum after collision. So I'm feeling lazy to write. So momentum before collision equal momentum after collision. After collision. So now you write your momentum. You know that this is what? Before. Before, this is the upper part. So this is the before, and this is after. So before, you have M1. That is momentum, because we know that momentum is equals to what? mv. So m1, u1, that's for the mass 1. Then look at the direction of their velocity. Velocity is a vector quantity. So since you are considering to your right as positive, then means that when you change the direction, it must be negative. So this one must be minus, because this is moving to opposite of your direction. So this one will be minus m2, u2. Another person can decide to go this way. Minus m1, u1, then this one must be plus m2, u2. At the end of it all, you get the same answers. So when you pick, because they are moving in the opposite direction, so when you give one as positive, the other one must be negative. Okay, so whichever way you want to go, you will get it right at the end of the day. So you have this, then we are saying that it must be equals to after the collision. Now, after collision, we have P1 is now moving to the opposite of how it was going. So it means that that is going to be minus M1V1. Okay, because that side is negative. Then moving to your right is positive, then plus M2 V2. Okay, so this is what you will get. Then whichever way you want to manipulate, you make, assuming like you know the masses of maybe you know M1, you know M2, you know U1, you know U2, and then probably this one you don't know V2, you want to find out. So you do that, then also do for the kinetic energy. Okay. Now I'm now coming back to what I said about the relative velocity. So look at the movement. They're saying the relative velocity. So relative means one minus the other. And this part is the approach. This part, you see that they are now coming to collide. So that's what we're saying, that the approach, the relative velocities of approach is equals to what? The negative of the relative velocity of what? After separation. So I'm going to write only the relative the velocities. So I will say that my relative velocity was U1 minus U2. Okay, that is the approach. Then after the collision, they are now separate. This is the second one, is the separation. So this is approach. They are approaching each other. And this part is they are separating from each other. This is separation. The bodies are separate. They are separated after the collision. Then relative means one minus the other. So I also take, look at, let me put my negative here because I said negative of it, negative of that. So negative in bracket. Then you have what? Please look at your sign wall. The sign is very important in collision. Don't miss your sign. So the first one, I took U minus U2. Okay, so here should be what? V2 minus V1. V2 minus V1. Okay, or if you don't want it that way, take U1 minus U2. So we also take V1. Let me write it here. I will show you V1. So U1 minus U2 equals to minus V1 minus V2. Then if I operate my negative sign on the bracket, I will have what? V2 minus V1. That is the side. But this will be positive and this one negative. So in that case, I'm going to have U1 minus U2 to be equals to V2 minus V1. Now, when I make, minus this. So when I divide this by that, so divide 2, I will have V1. So let's say I'm divided by V1. So I'll have U1 minus U2 over V2 minus 1. This is equals to 1. And this is what we are calling the coefficient of what? Restitution. Coefficient of restitution. Restitution. Okay, so that's what we are calling the coefficient of restitution. And in solving this, it's very easy. So like the example I was citing here, you see that after I've gotten this equation, so this is my equation 1. So this is my equation 1. Then I will use this method as my equation 2. Or better still, if you don't want to do it this way, you can leave it and use this one. Use this one. This one as my equation 2. So solving this and that simultaneously, by then you will know 3 of these variables. So from the question, initial velocity for mass 1 will be given to you. Initial velocity for mass 2 will be given. Maybe final velocity of mass 1 or mass 2 will be given, and you are allowed to, or asked to find the final velocity of the other. So once you know this, you know these two, you can easily solve for the third one here. So once you get that one, you quickly come and put it in this equation to get the other one that you are looking for. So that way is very short as compared to if you want to use the kinetic energy formula, that after getting this, you come and say half m1 q1 square minus half m2 u2 square, m2 u2 square to be equals to half m1 v1 square minus half m2 v2 squared. Then you solve this. This one will be like complex, and then making them the subject, it will be too complex. So you use that one. Okay, let me see if I get a question that I can just solve with you using this. So one thing you should know, for a perfectly elastic collision, the coefficient restriction is what? It's 1. And then for an inelastic collision, it's less than 0, because inelastic collision, the bodies move with a common velocity. And for that matter, kinetic energy does not conserve. Okay, so you can write it as the coefficient restriction is what? Speed of separation of particles divided by speed of separation approaching of particles. So it's the same thing. Either what I've written here. See, I am using approach and then what? Separation. It's the same thing if I also divide through by the approach. Okay, so you have E to be done. So it's not difficult. It's not difficult. Have you learned something, or you're still confused?
Yeah, I've learned something.
I thought I could have seen. Let me see. I will get a question, but I will give it to you too. To do it. Okay. So let me see this. On this one, they've given the description really difficult for you to solve. So I want a question. Another question. There's a question. Object A of mass this with initial velocity of this collides head on with this of mass this that is at rest. What are the final velocity A and B of the two masses? This is so this one you can solve it without imposing that condition. Okay, no, let me write it. I'll use it to solve it. So let's say example. So we have object A of mass NA. So object A of mass MA is equals to 10. 10M. Now this one I will not need this. I will not need this. With initial velocity of this. initial velocity. Let's see if velocity UA. Let's see what are the final. Okay, it's elastic. We can use it with initial velocity UA collides head-on with object B. Object B of mass MB is equals to M. That is at rest. What are the final velocities of? So what are the final velocities VA and VB of the two masts? Two masses. Okay, so solution. If you can sketch, it will help you. So you have object MA. So let's say this is MA. So once it's head on, it means that they are moving in opposite direction. So this one will MB. So head on collision is, so this one MA is equals to M, 10M. That's the mass. Then its initial velocity is UA. Then this one collide head on with objects B of mass MB is M. So this one MB is equals to M. But this one was at rest. Head on of this, that is at rest. Okay. So this is at rest. Okay. So once it's at rest, so U will be 0. Once it's not moving, it will be 0. Then what are the final velocities VA? So once you're given VA and VB, means that it's elastic. The collision is elastic. Okay. So I will use the two methods for you to see the difference, what I was talking about. So let me set some slides. So first of all, we go by the normal way of solving, and then we use the coefficient of restitution too. So here, since we know that the body separated after collision, so let me add that. So let's say after the collision, they move in opposite ways. So that's why I was saying that don't worry about the sketch. You can sketch it the way you want. So this one will be VA, and this one will be VB. Okay, so since it's elastic, momentum is conserved. So now follow your sketch. So you follow the sketch. So you have M A U A minus or plus, whichever way you want. So because the second one has no velocity. So minus MB UB. Is equals to MA. So check your first direction, you give this one positive. So this one must be negative. So minus MA. VA, then plus MB, VB. Look at the direction of B, which is going as the initial direction of MA. So that side is positive. So any other side must be negative. Okay, so we have this. Now let's make our substitution. MA is 10 M. So this will be 10 M UA minus 0 to be equals to minus 10 M VA plus the B has mass of what? M. So this will be M VA. Okay, so I can say that 10 M UA is equals to M VB minus 10 M VA. Okay, so I can make one of them the subject. Can make one of them the subject, or you leave it this way and label it as equation number 1. Then again, kinetic energy is conserved, so you go by the kinetic energy formula. So this is going to be MA half MA UA squared minus half MB UA squared should be equals to, now the velocity that is making this term to be negative, but once you square, so minus 1 square is equals to what? Positive 1. Okay, so it wouldn't change anything, so you can rewrite it as what? Half MA squared, then plus half MB VB squared. VB squared. So this is what you also have. Then we make our substitution. This we have 10 MUA squared minus 0 to be equals to half 10 MVA squared, then plus half MVB squared. So this will give me 5 MUA squared to be equals to half, no 5, sorry, 5 MVA squared plus half MVB squared. So we can cancel M throughout. Oh, this place to M is there throughout. We can cancel them. So here to the same thing, cancel M throughout. Okay. So when we do that, I can change this fraction by multiplying through by 2. So if I do that, I'll have 10 UA squared to be equals to 10 VA squared. Then that will now be plus VB squared. So equation 2. So now I'll solve these 2 equations simultaneously by making one of them the subject. Okay, so now I have 10A, 10 UA is this. So it means that where I have 10 UA, this is square. I'll substitute this, or better still, if you want, you just make the UA the subject. Okay, so you can do that whichever way you want, whichever one you want to divide through. So if I want, I will divide here by 2 by 10. Okay, and I'll have this side there. Or if I want, I'll make VB the subject by taking this to the other side. So let me do that. So this will be 10. I hope you are following UA, then plus I will have 10 VA to be equals to VB. So now I've made my VB the subject. So I will come and substitute VB in equation 2. So it means I will substitute VB here and square. So I'm going to square the whole of this. And that will make it complicated and then long. But let's go. Let's do it. You see the difference. So if I substitute star in this, I'll have 10 UA. So I'll now have 10 UA squared to be equals to 10 VA squared, 10 VA squared, then plus, instead of VB, I'll now put 10 UA plus 10 VB. 10 UA plus 10 VB, then everything square. So let's proceed to 10 UA square equals to 10 VA square. Then plus, I will square this, I have to expand this. So if I have x plus y, all square is expanded like this, x square plus 2xy plus y square. So I will apply this there. So it means I'll pick, this is my x, this is my y. So this will give me 10 square UA square. So that will be 100. So let me just write since you understand what I'm doing. So this will be 100. So 100 UA square. Then 2 times 10 times 10. That will be 20 times this. That will be 200. 200 UA UB. Then I'll now take plus 100 VB square. Okay. So yes.
Hello, sir.
Hello.
Sir, is it 200 UAVB or UB?
200 UAVB. Okay. So this is V. VB. Okay. So this is what we'll have. We need to group items. We have VA. We have another VA. I'm sure we've eliminated this. It's supposed to move. So let me come here. This is 10 UA, VB, and then VA. So 10 UA, 10 VA, okay, then VB, that's it. Then we have UA square, then we have VA square, then we have VB square. So UA, VA, okay, I think that is correct. So let's see whether we made the right substitution here. So 10 UA, 10 this and that. Okay, so can we cancel some 10 out? This is 100, so group items. So group items. So this is going to be minus 99 UA square should be equals to so this and then that, then UA VB, okay, to be equals to 200.
Sir, please, is it minus 90 or 99?
Yeah, I think it's 90 UA.
90. is 90. Then this is plus 100 what? VB square. 100 VB square. Okay. I think we still have to. Let me see. Up. My eyes are. I'm not still important. So we have this. I'm coming. Once we made a substitution, these terms shouldn't have come. It should be left with like two similar terms. While we still having three unknown terms. M MAUA MBUB BA. So this is 0. Okay. I think the problem with okay, so we introduce a 0 here. So this 0 is there. So we have UA, we have VA, and we have VB. So VB will be UA and VA. I think that's yes where the problem is coming from. We are not supposed to have VB again here. The problem is coming from here. Now we are substituting for VB, but I've written VB here again. That's why we still have three unknown variables. Have you seen what I'm saying here?
Yes,
Yes,
please.
So if we check the star equation star here, we are making substitution for VB. So that term, this term should be eliminated. So it would be 10 UA plus 10 VA. Should be 10 VA. So 10 VA, not VB. So let me do the corrections and we'll continue. So this is A. Then this is A. That is one thing about this formula. When you're going by this, or it take time, you mess up. Okay, so this one will be A. A. Okay, so you have this. This. All right. So we have, let me now rewrite it. So let me see it. So we now have what? Minus 90 UA square, right? Is equals to 200 UA VA plus 100 EA square. So,
Sir, please, I think it should be plus 110
110.
VA squared. There's 110 VA squared over there.
Now this one.
Yes.
Okay.
Plus
okay.
the one other.
Yeah, I skipped it. So this is 110. Because I took it from the correction. So this is 110. Okay. So now that we have this, so this is in the form of a quadratic equation. You can rewrite it in the quadratic form in terms of one of them. So let's say we are writing in terms of the UA. So UA square means that you are treating VA as a constant. Okay. So you write it as 90 UA square plus 200 VA UB then plus 110 VA square. So this is like AX square plus BX plus C is equals to 0. So you simplify it quadratically. Okay. So our coefficient here, A is 90. Our B is the whole of this. Then our C is the whole of this. Okay. So you simplify this to get A. So you get A into formula. So those of you with the calculators, you can point this one. You see that this is like too long. It's too long.
Very long.
So that is it. That's how you do it. But if you are going by the coefficient of restitution, so when you get here, the moment you come out with this relation here, you are good to impose that and then go. So I'll take it from here. So we have V 10 UA. We have 10 UA is equals to, oh yeah, 10 is equals to, not plus 10 UA plus 10 VA plus 10 VA is equals to VB. Okay. So let me say VB is equal to 10 UA plus 10 VB. Am I right? Yeah, 10 VB. Okay. So when you have this one as your equation 1, then you impose that the relative velocity of, for the coefficient restitution, the relative velocity of that is, so you take the U, so that will going to be, we are taking a UA minus UB to be equals to VA minus VB. The only way to recall is that when you are taking UA minus UB, when you come, the final should swap, the position should swap. So this one started with UA. Oh no, this one should be B. VB. Because we are saying negative of it. So VB, then V. And so this should swap, the position should swap. Okay, so when you have that, but already we know that UB is what? 0. So which means that our UA is nothing but VB minus what? VA as equation number 2. Then you substitute equation 2 into equation 1. So if you do that, we have our VB to be equals to 10. Then 10 is UA. In bracket, we have what? VB minus VA, then plus 10 VA. Then you expand. So VB will be equals to 10 VB minus 10 VA, then plus 10 VA. So this will cancel this. Then you know that 5 VB VB. Why this is still VB? UA minus UB is VB minus VA. Then UA is equals to VB minus VA from here. Okay. Then VB is equals to 10 into bracket VB minus VA plus 10 VB. And but why are we still having 10 VB? VB is equal to 10 VB. Doesn't make sense. Doesn't make sense.
So maybe we can check our equation 1 again.
I'm sure something is missing here. VB is UA and then VA. UA and then VA. I think that is correct. We made a mistake somewhere. UA, UB. Okay, that's fine. And this is 0 minus MA VA. So minus 10 and then VB. Okay. So we divide through by M. That is fine. So 10 UA is equals to VB minus 10 VA. That's minus sign here. So good light terms. So this goes and become positive. And this is correct. This is correct. Okay, let me check my relative. So we're also saying that this is equal to the negative of this. So it's the same thing of rewriting it as UA is equals to UA minus UB is equal to minus VA minus VB. So when you change this is minus VB. So positive VB and minus VA. So this is also correct. It's also correct. Then our UB is 0. Yeah, so if UB is 0, we have VB minus this and VB that I can't see, or somebody should look at it on the screen and see where is the error coming from. I'm not seeing the error, but you can have like VB is equals to 10 VB. That one there doesn't make sense because that is what we are looking for. If it is VB is equals to UB, they are fine. Or we are changing the terms. UA, B, this is that VB minus VB. That's perfectly correct. And 10. Where are we getting this?
I think where you wrote the VB is equal to 10 into bracket VB minus VA. And we have VB is equal to 10 UA, rather, UA.
VB is equals to
10 UA.
So here will be UA. Here. Yes, but our UA is this one.
Okay, the UA is VB minus VA.
10 into bracket VB minus VA plus 10 VA. So when we expand, we have 10 VB minus 10 VA plus this. So this one cancel. That is, where is the error coming from here? So let's look at this one first. MA UA minus MB UB is equals to this. So this is 10 UA and this. So 10 UA plus 10 VA is equals to VB. At level 10. So the VB is 10 UA plus 10 VA. 10 UA plus 10 VA. Yeah, so this is correct. So UA minus VB is equals to VA minus VB. So UA is VB minus VB. I can't even see.
Hello, sir.
Yes.
I suggest we have seen the concept, so
We should move on.
We can move on and we'll tackle it later.
Mm.
And I have a question here.
Okay.
Please, for the momentum aspect,
Yeah.
you say in the book we made it the initial plus, we made them pluses, but we did have some part minus and some part positive. I don't get it.
Yeah. Okay. So let me go back to where I sketch here. You mean here, the equation that I'm writing?
When you were here, conserving the momentum, the first.
Yes. So that's why I mentioned that it depends on your sketch. So you will follow the sketch that you sketch in your book or wherever. At the end of it all, you will get the same answers. So probably, let's assume that what is in the book, we've not seen it. Not everybody have seen it that way, and you have decided to sketch it in your way, whichever way you want. At the end of it all, we all have the same answers. So if you look at my sketch and what is in the book, they are not the same thing. There, after collision, you will see that they are following each other. Is that okay?
Okay.
And their mind they are moving in the opposite direction. So that is why you see that in the book they are using plus and I am using what? Negative. So it depends on your sketch. Depends on the sketch. I'm sure we are missing some terms somewhere. That's why we are not getting. But at the end of it, we should have gotten the answer.
All right.
When you use this is like very short as compared to what we were going through. That one is very, me myself, I don't like using this approach. You do it and then you even become confused. Okay, so anyway, that is how you apply the coefficient of restitution to solve problems of this nature. Maybe when we are done, and then I will look for questions for us to solve, and maybe we see some. Okay, so I'm not sure you've done the moment, couple, and then talk. Have you done those things?
No, please.
Okay, so that is where we moved. We'll just work you through that one. I wanted us to finish with this chapter today, but look at things. We may not finish, but I'll see. Some things are there, we just have to go through them, not. Okay, so sorry. We've not even gone for a break. Do you want to take a rest small and then come back, or we should continue?
Sir, let's finish it. Please.
Moment, couple, and then talk. Okay. So that is the next thing we want to look at. And these three concepts are also interrelated. They are related. Now, when you talk about a moment is a force times its perpendicular distance. So when you have a force acting on an object at an angle of 90, okay, so when you take the force multiplied by the sine of the distance times the sine of the angle between it, that will give us our moment. Okay, so when you pick the moment, you define as moment is what? Moment is the product. Is the product of a force times its and its, let me just put it that way, and its perpendicular distance. Okay, so the moment is normally written like some books you see I, we use I for it. It depends on the books that they're using. So it can be written as this. So force times D. Okay, so when you add the distance, so that would be sine theta. So let's say we have a force that is acting this way. Then we have a distance that is making 90-degree angle to the direction of the force. So it means that the force is acting from behind here. So this form a 90-degree angle. Then the distance of this is t. So since it's a 90 degree, that's why you have this. So you have that moment to be written as force times distance. So since we know that force has a unit of Newton and distance has a unit of meter, so the SI unit of moment is what? Newton meter. That is the SI unit. Now, when you have a pair of two forces acting at the same angle, that will now bring us to what we call the couple. So this is a force, and this force, another force. So F1, then F2, acting at this. Okay, so these are two pair of forces. So this is what we call the couple. Okay, that's the difference between the moment and then the couple. So for the couple, you're having two forces, two pair of forces that are acting at an angle, 90-degree angle at a distance. So by that one too, you still use a single force because this would be like this whole distance. So when you consider this force F1, the force is acting here from here. This is the distance. So this D is from this point to that point. But also consider F2, the force is acting this way. So the distance also from this to that point. So at the end of it all, you will get the same thing. So when you use the F1, you also use the F2. That is provided if the force has the same magnitude. So the moment of a couple is of a couple about a point boiling point is a product of one force and the perpendicular distance. Okay, so you have the moment of the couple expressed like this way. It's equals to FD. From the diagram that I sketched in the previous slide, you have this. And the same way, it is a unit the same thing. Now, the torque is when the force acts on the object and the object rotates. Okay, so the object is now rotating about its axis or a pivot. So that will bring us to what we call a torque. So torque has to deal with what? A rotating axis. So and an example of a torque is when you are losing a knot by a spanner. So that when you use a spanner to lose a knot, there is going to be a rotation of the spanner about the axis because they know that to be losing. Okay, so in that case, you have your torque that is acting vertical, and this is a fixed point. That's a pivot, the turning point. So this is a turning point. Then you have your R down because of the force that will cause this to rotate through an angle. So let's say theta. So this will cause this to rotate at an angle of theta. So this would be the force. And then your torque star will be represented as shown here. Okay, so just as I'm saying, so let's say we have somewhere here, then we attach our spanner here. Then when we apply a force on the spanner to use the bolt here, now the torque will be exerted as shown, like because of the diagram. That's how you see. You may not understand the diagram, but in reality, just think about losing a nut on something with a spanner while the spanner is causing the knot to rotate as a result of what? An applied force. So you will write the torque as this. So the expression for the torque is equals to the force times the distance r, then sine of the angle theta between them. Okay, so the r is always perpendicular. That's the perpendicular distance. So we have the torque equals the perpendicular distance, the force times the perpendicular distance times the angle that is in between the force and the distance. So in brief, that is about the torque. Then you will now have it like in a situation where the torque is being, like whether it's applied on a rotational body, apply on a linear object, or it causes the body to rotate or to move linearly. But these are the formulas you are supposed to know. All these things are just change of variable. Yes.
Yeah. So with the movement and that of the couple, I think that the couple is dealing with one force and the movement is just a force. Because if you look at the definition,
Yeah,
it's just they're almost the same. Just that this one deals with one force. The
yeah,
couple is
yeah,
one force and each person.
yeah. They are same. But the only thing is that for couple, you are using two forces. So two forces to cause an object to move. But if you take one of the force, it's the same thing as like here, what I was saying here. See from here, you are using like the bicycle uh, cram where you are paddling. When you are paddling the bicycle, you see that it's something like that. So that one constitutes a couple because you are applying two forces. But the turning point is somewhere inside the bicycle. That's the middle. So you see that there is a bar, some white bar that is passing through the whole of the bicycle, linking the bar that the pedal is where you place your leg on, or better still where you place your leg on, and then that white bar down. You see that they are perpendicular. By now, if you want to get the amount of force that you are using to propel the bicycle or to let the bicycle clamp rotate, you pick one of the force. That is either the force that your left leg is exerting or your right leg is exerting. At the end of it all,
Hello.
Yeah.
I thought
So
I
I
was
say
on
had
mute.
a no, the network from say.
Okay.
That patient are you there?
I think he's off.
This cause God will help us.
It's not easy, bro.
As as well, the feel sleep, bro.
And then go sleep. Oh, you can't kill yourself. Go bed.
Newtonian. As the class ended, looks like everybody is leaving.
No, it's not ended. I think Seth's network is not favorable, so he's free to
We are
session.
waiting for him.
Okay.
Hey, don't go.
All right. So, Selaki, your hand is up. Let's listen to you.
Oh, sorry, the mistake, sorry.
All right.
Okay, sorry.
This is even Unit 4. The talk is Unit 4, Section 4 of Unit 2.
Yeah, we are. You know,
Five
unit 4 and
six.
the reading assignment.
Uh,
The proof we will do. The proof is the consecutive analysis. That's why I was asking, is it for one question or you will have babies in case it comes?
Master, such a question,
Question
don't
back to say,
tackle it. It wastes your time. Don't tackle it.
That is the issue. Just look
so
at the
that's
question we
that,
just did, but we could not arrive at an answer. That one self no be
but
easy.
For that one, it's simple.
Yeah.
It's
good,
not complex.
questions.
What Seth was saying, just not use the kinetic energy one. Use the relative velocity one.
Okay.
In addition to the momentum. And
Okay.
when you go and you sit down, you see that you get it. You say you're working under pressure, so we might be lost somewhere. As I pentam say, we are the no, say Nankasano. Besanko speedy and so tunable. Anything. Yeah, he's doing well.
He's doing well.
Teaching is perfect.
I think the scheduling of another time for us to meet him.
I think we should
do it.
Yeah.
We should discuss it now and inform him so that he will be aware and he will schedule his time so that he will meet us. If you wait and see Monday or Tuesday, we'll discuss and inform him. But
I think it may also happen
might
that
also
the
be
time we would
busy.
set.
So let's do it now. What? Yeah.
Let's wait. Wednesday another Tuesday. Between the 2 days. Which is your Wednesday? That is my suggestion.
So in case Serabi also fix his on that date too, what do you do?
I mean for him, he know decided yet. He said he will fix it for us.
Okay.
Yeah. So
when we fit for this one, when we fit this one, then when he fits it, then we tell him that he can see his own.
Okay.
Yeah, we can do that. We can fix it on Tuesday. Then we inform Sarah that Tuesday we will be busy, so you can fix it on, let's say, Wednesday or Thursday or Friday.
All right. So let's go by the Tuesday, the time. The
Tuesday
time should be at a person.
So like 4 o'clock to.
Yeah.
It's 4 o'clock. Okay.
Let's do 2 hours and another something like, it's 2 hours too much.
Now and then you start at any time that you close.
So Mama calls.
Yeah. It is well.
So let's make it 4 o'clock.
Yeah, but I think
Some of us
we did not help ourselves. We did not help ourselves, especially those of us doing physics, because on the platform we saw that the chemistry, the biology people were meeting. At least we could have also scheduled the time that we were in the house. Now school has even reopened.
Please don't stop and I just return.
Bro, it's not like that. It's here. Sometimes when we share the people who are supposed to do it, maybe they will be engaged. Ibab. I thought of that, but someone like say Rabi like this is a busy man.
Please,
Yeah.
as the class ended.
There was a time.
No, we are waiting for the lecturer to join.
I understand, but I feel like the way they are busy, if you schedule and they are, it's not matching with their schedules, it will crash.
Okay.
Something like this. As last week, there was one master who scheduled a class with us, but later it didn't happen. So it means that most of them
Okay.
are busy. Yeah. So this one, since he said, he said we should decide that we will do for us. Then I think this one to happen. So we should all agree either Tuesday. If it's Tuesday, then Tuesday. Then we'll see the way forward.
Even if we do not agree, we are going to lose. So because this one has even ended. It has ended, but we have a lot of units and sections to cover.
It's
So we
true.
definitely have to be kind. Mm-hmm.
Myself, this week
Because
I will go to my village. My village, like the network is a crying network.
mm-hmm.
I no report. I not go at my station yet.
Okay.
Tomorrow I will go in there. So let's see what the Lord will do.
So when he comes back online, we will call him at Tuesday 2:00. We want to meet.
Okay. Okay. Thank you.
As to whether his network can even permit him to come back, because we are supposed to end 3:50 and it's almost 3:20. As to whether his network.
Uh, but even if he doesn't come, I think the coursework can inform you, or we can WhatsApp him that we can make it on Tuesday.
All right.
Let me bring this thing. You see, there was a time that that was last week. I think we asked, Franco to prove the ferment principle with the refraction and put it on the business.
Yeah, the Fermat's principle.
I don't know. There was this thing that I saw. It's almost similar to the other one, the reflection or something like that. But when you end it, you only use the is it n the refractive index equal to what. I've looked at the format. It's almost similar. You prove it as the form the first one. Then the ending part you use some two steps like that. Then you end it. I don't know. I saw it, but I was
Okay, I
waiting for
think
Fran to put one on the
Sir has
platform. Then
joined.
I'll see. That is the same thing.
So Sir has joined now. So now.
I think I was
Okay.
offline for some time.
Hey, that's a Benjamin.
Hey, I went online and offline without knowing. When I was explaining this part, were you there?
Yes, please.
Okay. So I was saying that the omega is the angular velocity, and it came from this part. As I was asking whether you done circular motion in your first block physics. So there you have like angular displacement, that is theta on time. If you get angular frequency of velocity. Okay, so that is the power. All right, so now we've learned linear momentum. So we'll go and look at what angular momentum is. But before I move to that section, any question, please?
Please, are you done with the talk, couple, and
yes. Yeah, so see, the talk is like the work, energy, and power that we've done. So we are transferring that knowledge to the talk, because we know that talk cause an object to do work. And so the other thing is, when you know what a talk is, then what is the expression for a talk? Okay, so when you know the expression for a talk, then what will be the work done if a talk of this amount apply or act on an object to cause the object to rotate about the pivot or what axis? Then you write the equation. So from here, that let me start summarize all that set from that one. This somewhere here. Here. So we are saying that the moment is forced at a particular distance. So here I'm using the angle as 90. So 90 sine 90 is 1. So you come back to empty. That's a particular distance, and that is moment. So for moment, you have a force that acts at an angle to a distance perpendicular to it. Then when you come to the couple, you have two moments, that is two forces that are acting at an angle. You see it? Okay, so you have two forces acting at an angle. That's what I explained. So this constitutes a couple. Then the torque, as I mentioned, torque causes object to rotate about their axis. Okay. So a rotation object constitutes a torque. So when you write the torque is written as the force times the perpendicular distance times the angle between it. Okay, so let me take, yes. So you have something like this. Okay. Now I want to see what is the work done by a torque. How much does a work said to be done when a torque is acted upon an object? So we write our work done. We already know that work done is what? Force times distance. So when you're writing in the integral form, like this. But since the torque is not causing the object to move linearly, but in a rotation form, so the R, which is the angular part, because it's going to be rotated. Okay, so that will be R theta. Have it this way. So that will be the R. So when we substitute that one in place of it, we give us this expressions. But we know that this whole thing is tau. That's tau. This is tau. So in place of this, we put our tau there. And then the torque is now the work done will be dW on that. So when you integrate both sides, you get work done to be equal to torque times what? The angle. Then we come to the next slide to look at the power that the torque can be transmitted. So we are done with the work done. So the work done equation is what? Work done by torque. The equation is the torque itself times what? The angle. Then what is the power? You know, power is what? Work done divided by time. So when we divide our work done by torque by time, it gives us the work done and the power by the torque, or the power transfer here by what? The torque. So when we do that, we find the theta on the t, and this is what I'm saying, that it's a velocity, angular velocity, and it's angular velocity because the object is rotating. It's not even straight line, so it's rotating. So that's what this one is coming. So it means that power can be expressed as what? Torque times what? Angular velocity. Okay, that is the power that the torque will transmit on an object. So that is the expression of. Okay, so we now look at the angular momentum. It's the same momentum. Once you know what momentum is, the same thing. Momentum. So we are dealing with momentum, but this time around, we are looking at it in the circular path. Okay, so we are looking at the momentum, the circular path. So the idea is still the same thing. So that is why we have a linear motion and then what? Circular motion. What is the motion of an object moving in the straight line? And then the motion of an object moving in a circular path or circular track. So the same thing here. We already know the momentum for a linear to be equals to what? mv. So we want to look at the momentum of an object if the object is moving in a circle. Okay. So the concept is still the same thing. Just that we are changing the path that the object will be moving. Okay. So here, because talks about an object moving in the circular path, so we are linking the torque and then the angular momentum here. So if we have our Cartesian plane with three coordinate system, as usual, our z is here, we have our x here, and we have our y. Now, if we have an object that has a position vector, so let's say object is, so bear in mind that we have this line. Okay, so we are looking at it in 3 dimensions. So this is a sector. So this is the position vector from the center to the circumference. This is the arc. Let me sketch it more. Make it straight. Okay, so this is our arc, which we are always calling the position vector. Now, so from this arc, if we make a tangent here, so let's say the object is somewhere here. We have an object here on this point. Now we have another major line passing through the object towards it. So definitely there's going to be an angle between. So this is 2 point P. So there's going to be an angle between this line, and that will be the angle of rotation theta. So you have that there. Now, if we write this, P is equals to mv. That is for the linear case. So the product of the mass and it gives velocity. Sorry, and the velocity is given by the momentum. Now that we have the angle between R and P, okay, then we can find the value of something. So this is the L. We call the angular momentum. This L. The L there is the angular momentum. So we can find the angular momentum. Find the angular momentum by taking the cos of it. So that would be L will be equals to R cos P. So R cos P. That will give us our angular momentum. So okay, so you can write that one as our angular momentum. Then when we differentiate by applying the product, okay, you know when you have two words or two letters that are multiplying and they both depends on they're all dependent. What you do is that you keep one as constant, differentiate the other one, then you add it to the other one, then keep it as constant and you differentiate respect to the second one. So we can apply that. So when we do that, so we say L on T will be equals to here. We are coming to keep P constant. So we have PL on the T times P plus. They will also keep R as constant. They also differentiate the P respect to P. So we can have that. So after doing that, I will simplify our dr on the T. Then this one be times. Then momentum is mv. Let me write that one. Plus we have R. Then we have times P on T. So we have this expression. So if we go further, you can say that our L DL on the T will be equals to, now the T, the R dt is velocity. So V. Yeah. This is velocity, the R dt. Velocity. So I can write that one as, so I have P cross MV. Then plus I'll have R. Then I have cross the T, P on the T. So if I factorize my I'm sorry. Okay. Okay. Yeah. So if something is M in bracket B cross U, we factorize it. The getting some expression is not right because there's no M that should be factorized. Let me see. And I got some. Let's leave M here. This is M R cross that. That's M here. So that's M. So since there was M here, so when I factorize this M out, we have V cross V plus R cross the P on the T. But velocity would be equal to 0. Means that they are all along the same direction. Remember when we're dealing with the I dot I is equals to J dot J is equals to 1. But I cross I is equals to J cross J is equals to 0. Okay, so we're applying that principle here. So this one will give us 0. So which means that this term will go to 0. We are left with this part. So it means our D L on the T is equals to R cross P on the T. That is what will be left. But from the Newton's second law, we established that we realize that P on the T is equals to F. We saw this one previously. So we can put that one there. So we can say our D L on the T is equals to M is equals to R cross F. Okay. So we can see this one. I will differentiate the angular momentum. Then, but R cross F or R times F is nothing but what? Torque. So it means the differential of the angular momentum is nothing but torque. That means when you differentiate angular implies that the differential of the angular momentum gives the torque or produces the torque. Okay. So that is a relation between the angular momentum and then torque. So you first of all write your angular momentum. Angular momentum is equals to M times R plus P. Then you differentiate, applying the mathematics to get the relation. Okay, so that is the torque. So one thing you should know is that the torque is what? The turning effect of what? The force. Okay, torque is the turning effect, the effect that you get when the force turns an object or causes an object to rotate. It's a torque. So we can also conserve the momentum, the angular momentum. Okay. Since we conserve linear momentum, we know that from the principle of conservation of the linear momentum, we said momentum before collision is always equals to the momentum after the collision. So in case of the angular momentum, if the external torque acting on the particle is zero, then the angular momentum remains unchanged. So from the equation that we have here, if the torque is zero, if this torque is zero, it means that the angular momentum is what? Unchanged. Remains constant. So that is the conservation of the angular momentum. So for the angular momentum to be constant, and the torque must be what? Zero. So the moment torque is zero, that's right. The angular momentum is constant. So the principle so that is for the conservation. So you can also be given a question to find the torque. So for instance, a particle moves in the central force field given by F is equal to R square R, where R is the potential vector of the particle. Prove that the angular momentum of the particle is conserved. So we should prove that the angular momentum of the particle is conserved. So we have to have the torque to be zero. So do that by equating into zero. So when you equate and you get the cross product is given. So that's the torque conserved or the angular momentum. Okay, so we have 12 things. So 12 things, let's look at the last thing. Yes. You know that we are done with this. Yeah. So here, the contract such for a long time. I will just introduce this one again. I will come back. Right. Right. So central force. Central forces. So when you mention the word central forces, it means that the forces that are acting on the object are concentrated in the middle. So the forces are obtained by looking at the center or the central point of the object that they are acting. So you need to balance those forces. So if you cast your mind back, we talk about this bodies, like when you are taking some bodies, some objects. So we have to find the center of gravity where it is acting. So we take a rectangular object, you draw lines on the diagonals to meet where the lines intersected. So what we will term as what the center of that solid figure. So in that for a rectangle or a square object, it has a high center of mass. So it is highly difficult for that object to fall down if the center of gravity is outside. But if you take a triangular shape, then when you put the base down, so like this. So if this is a triangular shape, so we will draw lines like this. Oh, sorry, where the lines will intersect. So you consider as your strength. So this one, if the center of gravity falls out for this to be 4. So the following will be as if you let it stand on this. So let it stand on this. So this is easy to fall. Easy to fall that is. But if you take a rectangle or a square, so if this center is located in the middle, it cannot really fall. So the central forces, let's talk about the point at which the forces are acting. Talks about the central part of the object. So level 8 minutes, but like I'm tired. So let's pause here and use the remaining time as our break time, and also to conclude on when we have our next class.
Hello, sir.
Yes.
Yeah. When you went offline, we concluded on the next meeting. That was, we proposed Tuesday, 4 p.m. I don't know if that one will be suitable for you.
That's not bad. I don't really have any on that time for now. My there is knowledge, but let's fix it at that time. I have not had anything that we have at that time. So
Okay, sir.
if I
Okay.
I will let you.
Okay.
Okay.
Sir,
So
please, apart from the book, do you have any simplified slide for us?
the slide will give you, apart from what I'm teaching, though I use the book, but I don't
Oh,
take everything from the book. So that's the only thing. What I will give you is more complex than the book. So, but what is that questions are set from the model. Those are questions outside. So you guys try and understand all these things that we are going through. That is how based on our examiner. So not that we will teach the manual, the model, and then questions will be set outside the model. I guess that there are petty things that when you are reading, you don't take notice of. There are the things that you go in and see, and then you not recall them. Because it's a quiz, for instance, it's objective. So when we are setting objective question, we don't just set it straightforward. Even if we set it straightforward, but the answers will be similar. So when you don't read very well, you will see it and then you wouldn't know which one is the right answer. If the answer is 2, you see the 2, but you see positive 2 and negative 2. So you will now try as much as possible to see the answer positive 2 and negative 2. You see 2, 2. Okay, so that is it. So let's revise all that we learned and then the model. Now, the quiz is next week. And next week, sorry. The next week will be the practical. So,
Okay, sir. Thank you very much.
all right. So let's pause here. What will we Tuesday? Have a great weekend.
Okay, bye-bye.
Bye.
Yeah, hello, colleagues. I was off. I don't know if you were able to tell him you meet the Tuesday, like we said.
Yeah, we informed him and he said he has nothing to do on that day, so he'll try as much as possible to meet us.
Okay. So did we set time? Time.
4 p.m.
All right. All right. Thank you.